Hello everyone, it's a pleasure meeting you all in my mathematics class. I want my viewers to subscribe for my YouTube so that you will be able to all see all my videos in the present videos and also the forthcoming videos, which are going to be definitely useful to all who study in either engineering or in arts college or even for the plus 2 students. Today, you see that I have chosen a set S, which consists of only 3 elements, 1, 2, 3, and I go for all possible permutations. Permutation in the sense that, see, the first place you see that this is 1, 2, 3, I go for a permutation of that. That means I go for a mapping. It is also a permutation, is also otherwise a mapping also. You see that 1 is mapped onto 1, 2 is mapped onto 2, 3 is mapped onto 3, this is 1. And this first place is, that means this you can fill this first place by 3 different ways, either 1 or 2 or 3. And the second, and having filled the first place, you can go to the second place, which can be filled in 2 different ways because the left out elements are 2. And the last place is only 1. That means the first place can be filled in 3 ways, second place in 2 ways, and third place in 1 way. So the total number of ways of getting different permutations are 6, not more than 6 at all. Now those permutations are nothing but, as I told you, they are nothing but the mappings from the set 1, 2, 3 to another set which we map as 1 is mapped onto 1, 2 is mapped onto 2, 3 is mapped onto 3. This is an identity mapping. And 1 is mapped onto 2, 2 is mapped onto 1, and 3 is mapped onto 3. This is another mapping. This is another permutation. And likewise, you see that the 6 permutations are written. And 6 permutations are nothing but the mappings from the set 1, 2, 3 to another value of God 1, 2, 3 in all possible ways. Thereby, you are getting 6 permutations. After then, what I do is, I collect what are the permutations here? E, alpha 1, alpha 2, alpha 3, alpha 4 and alpha 5. Now, I define a composition. I define the product of 2 permutations by the operation star, and the star is the operation which is nothing but the product of 2 permutations, which is nothing but the composition. That is the composition of mappings. That is, you see that if you take alpha 4 and alpha 5, they are the 2 permutations. If you operate using this star, using this star operation, what is it? Is nothing but your composition of mappings. That is 1, 2, 3, 2, 3, 1. 1 goes to 2, but 2 in turn goes to 1. So 1 goes to 1. 2 goes to 3, 2 is mapped down to 3, but 3 is mapped down to 2, therefore 2 is mapped down to 2. And 3 is mapped onto 1, whereas 1 is mapped onto 3, so 3 is mapped onto 3. So there you see that alpha 4 star alpha 5 is nothing but your identity mapping. Okay, this is called an identity mapping because 1 is taken to 1, 2 is mapped onto 2, and 3 is mapped onto 3. Okay, now and another example is alpha 2 composition alpha 3. Alpha 2 composition alpha 3 is alpha 2 is here, alpha 3 is here. Now 1 is mapped onto 3, whereas 3 is mapped onto 2. I got here, see, 3 is mapped onto 2. And 2 is mapped onto 2, 2 is mapped onto 3. And the last one is 1. And you see that the composition of these 2 mappings, which is nothing but the product of 2 permutations, is nothing but 1, 2, 3, which is nothing 1, 2, 3, 2, 3, 1. 1, 2, 3, which is nothing but alpha 4. Likewise, I go for the product of permutations in all possible ways. That is, E into everything, alpha 1 into all other permutations, alpha 2 into all other permutations, alpha 3 into all permutations. I go for that. Okay. Now, this, what I am going to do is, see, what I am telling you is that I take this S3. See, I take this S3, which is nothing but E alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. Now, let us prove S3 alpha is So let me prove that this is a group. So for which, as I told you, I may go for the products, all products, let us not bother about that. Here, what I have done is, I have taken this S is equal to 1, 2, 3. I have coined all possible permutations, and these permutations are nothing but the mappings, and I define a star operation and collect all the permutations. There are 6 permutations. One is the identity permutation. That means every element is mapped onto itself. That's identity permutation. Besides that, you have got 5 permutations. So totally 6 permutations. There are only 3 factorial 3 possible. Okay, factorial 3. The number of permutations are 3 factorial permutations you have. 3 factorial. Now, if there are 3 elements, 3 factorial permutations. If there are 4 factorial permutations. So you see that, then I collect all and put it as a set S3. So S3 is nothing but the what? The set of all permutations obtained on account of the elements S is equal to 1, 2, 3. So these are my permutation set. This is a S3 permutation set, and I define the star operation in this way, and I am going to prove that this is a group. So this product of 2 permutations are carried out, and I have prepared a table for that. That means a permutation table has been prepared by multiplying. I take these 6 permutations and go for all possible permutations. So I have prepared a table where the product of all possible permutations are taken. Now, so what is that I have done? S is equal to 1, 2, 3, and I have taken all possible permutations. Since there are 3 elements, factorial 3 permutations are possible, and I put them in a set S3, that is a E is identity mapping, that is a permutation, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. I consider this set, then I define an operation star, which is nothing but product of 2 permutations, that is composition of mappings. Now I am going to prove that this S3 star is a group. That's all I do. Okay. Now you see that, as I told you here, I have see this composition table with respect to star. Star is nothing but the product of the set. So you see that S3 star is given. So I have taken this, I have multiplied 2 permutations. For you see that alpha 2, see for example, alpha 1 into alpha 1 will be E. Alpha 1 into alpha 2 will be alpha 4. If you go for the product, as I have explained to you in detail how the product is carried out. So it is nothing but composition of mappings. So if you carry out the operations in the same way between two permutations, you will find that these are the resulting permutations. That is, for example, alpha 4 A star alpha 2 is nothing but the resulting permutation is alpha 1. Likewise, alpha 4 into alpha 4 will be alpha 5. Alpha 4 into alpha 5 will be E. Alpha 5 into alpha 2 will be alpha 3. So likewise, I am getting all possible permutations, resulting permutations. Know that there cannot be any permutation which can go outside this 6. It cannot go any permutations outside the 6 permutations. Now, I want this to prove that this is a group, S3 star is a group, for which the first property that we have to do is check whether its a closure property is satisfied. It is very well satisfied because alpha I star alpha j is equal to some alpha k, and this alpha k is after all an element of S3. Say alpha 1, alpha, you give any value for I and j. I and j what? I is equal to, see it is, you can take this to be, it is your, see 1, 2, 3, 4, 5 and E. And j also like this. J equal to like this, and k will be a resulting which will be in. So you multiply this, k will be another this one which will be in. So alpha I plus alpha j plus alpha k is for all I and j. So this is for all alpha I, alpha j belonging to S3. So this property is good because you see that this table gives you the full picture. You take any two, let I is equal to 3 and j is equal to 4, you see that you get alpha 1. So thereby we see that the closure property is satisfied. So this is what. Associative property, if you just check it up, alpha, I will just check it for 1. See, alpha 1 plus alpha 3 star, this is star, alpha 1 star alpha 3 star alpha 5, alpha 1 star alpha 3 star alpha 5. What is alpha 1 3? See, 1 3 is alpha 5, alpha 1 3 is alpha 5. So alpha 5 star alpha 5, alpha 5 star alpha 5 is alpha 4. Now alpha 1 star alpha 3 star alpha 5. So alpha 3 star alpha 5. What is 3 star 5? 3 star 5 is 2. So this is alpha 1 star alpha 2. Alpha 1 star alpha 2 is alpha 4. See? 1, 2 is alpha 4. So I am giving a verification. So this associative property holds good. True for alpha I star alpha j star alpha k is equal to alpha I star alpha j star alpha k for all alpha I, alpha j, alpha k belonging to S3. So for all alpha I, alpha j, alpha k, this associative property holds good. So this is now this becomes a semi-group. As I told you, I have explained, this becomes a semi-group. This is a semi-group. Now, you see that this is the now existence of an identity element. What is that identity element? An identity element is an element which when operated with other elements using this star, because what is the star operation here? Star. Under star, if you are going to operate that element, if you call the one you call as the identity element, with any other element, the resulting element must be the same. For example, you see that E is nothing but 1, 2, 3, 1, 2, 3. What is your E? E is identity element 1, 2, 3, 1, 2, 3. Now you see that you multiply with any element, E into anything will be 1. For example, you see that you take E into, I will call it as say alpha 1, if you take it as 1, 2, 3, 1, 3, 2. Now you see that E star alpha 1 is equal to 1 goes to 1, 1 goes to 1. 1 t is taken out, 1 is mapped onto 2 is mapped onto 2, 2 is mapped onto 3. So you see that you are getting this, which is again alpha 1. That means any alpha I, see, E star alpha I is equal to alpha I for all alpha I belonging to S3. So you can see this, I is equal to 1 to 5. So any element you take here, you see that E into anything is itself. Therefore, this identity, see E into alpha I, whether you do it in this way, alpha I into E, alpha I into E, or E into alpha I, E into alpha I is equal to alpha I for all alpha I belonging to S3. Therefore, the identity element exists. Then you see that the existence of inverse. If you want to check for inverse, you check this alpha. So this is go there. This is E. Go here. This is E. Go here. Alpha 4 is here. And Fi. That means for alpha 1 is C. Alpha 1 star alpha 1 is equal to E. And see alpha 1 star alpha 1 is equal to E. And see 1, 2, 3, 1 to 1. See alpha 1 into alpha 1 will be E here. If you check this alpha 1 into alpha 1, it will be equal to E. Check yourself. Alpha 1 star, that is alpha 1 star alpha is equal to E. Whereas alpha 2, see alpha 2 star alpha 2 is equal to E. And alpha 3 again, alpha 3 star alpha 3 is equal to E. Whereas alpha 4 star alpha phi is equal to E, and alpha phi star alpha 4 is equal to E. So this is what we do. That means here we see that these are all called the inverse. That means the inverse alpha 1 is alpha 1, inverse of alpha 2 is alpha 2, inverse of alpha 3 is alpha 3, inverse of alpha 4 is alpha 5, inverse of alpha 5 is alpha 4. So you see that for every element you find the inverse of it, and it belongs to the set also. That means now the closure property is satisfied. I have told you, because this matrix itself tells you that the closure property is satisfied, because product of any two permutation is again a permutation lying here. Therefore closure property is satisfied. Associative property, I have proved how it is. This is true for all. Therefore alpha I star alpha j star k is equal to alpha I star alpha j star alpha k for all alpha I, alpha j, alpha k belonging to S3. And this is E is the identity element, that is identity permutation 1, 2, 3, 1, 2, 3. So you multiply with any element, it will be the same. Alpha 1, say alpha 1 into E, alpha 1 into C, E into alpha 1, E into alpha 2, everything will be itself. Therefore identity element is established. And for every, see here is just round off all this E. Therefore this E happens to be your identity element with respect to this star. Therefore alpha 1 into alpha 1 is E, means alpha 1 itself is the reciprocal. Alpha 2 into star alpha 2 is E. Alpha 2 itself is reciprocal, that is inverse of alpha 2. Alpha 3 E means alpha 3 itself is the inverse of alpha 3. Whereas for alpha 4 it is alpha 5, and for alpha 5 it is alpha 4. So the identity, that is the inverses exist. Therefore S3 comma star is a group. And you will find that, see here I will just write this. See, you just check only this. Alpha 3, see, you will find that the alpha 1 star alpha 2 will not be equal to alpha 2 ij. I will write it here. Alpha I star alpha j will not be equal to alpha j star alpha I. You will can very well find. Say for example, if you take this, see you can check yourself. You just check whether alpha I star alpha j is equal to alpha j star. See, I will write it here. Alpha I is not equal. This is not. That means commutativity fails. That means it is not commutative. Star is not commutative. Therefore, it is S3 star is not an abelian. Is not a verify. So this you will verify. See, verify this. So verify. That means you have to check whether alpha any alpha 3, alpha 2 should not be equal to, even if it is real for one. So for some alpha star alpha j may be equal to alpha j star, it may happen. This must be true for all. This alpha I star alpha j is equal to, must be true for all. If it is true for all, then commutativity holds good. Even if it is fails for one I and j, it is not a commutative property. So for some, maybe we see alpha I and star alpha j may be equal. They may, see, this may be equal for some. It may be equal to alpha j star alpha y. For some it may be true, but even if it fails for one, then it is not a commutative. So this can happen only for some. It may happen. I am telling you, it may happen for some, but it has to happen for all ing, then only it will be called as a commutativity holds good. But here you will find that there may be at least one which may not obey this commutative property, and therefore this is not a commutative group. Okay, so I am just writing out, just verify whether this is true for all. Alpha I star alpha j is equal to alpha j star alpha I. You take every this thing. Don't take this identity element is not required. You take the rest of the elements and do the try to work out this alpha I star alpha j. See whether it is equal to alpha j star alpha I. If that is true for all ing, it is commutative. But there can be at least one which will not obey that commutative property, and therefore I am telling you that this is not a commutative group or a abelian group. This you will verify. We can just verify from the example that I given. Okay, thank you.